Thank you. And I had a text saying that the link is not working. Therefore, I was trying to check it. And good morning, everyone. It's my pleasure to welcome you all for the next roundtable. So, our second roundtable of our working group titled Seeking this Digitalization in EU funded Hydropower Projects. So, I'm very excited to moderate the roundtable, and I'd like to start with thanking you all again for being here and for attending online. So our working group is named Technological Evolution through Innovation and Digitalization. Pavel Rudolph online and me, Doğan Gezer, we are leading the working group. And this session, this roundtable is a part of our ongoing works under working group number 2. And today we will discuss the digitalization issues on EU-funded hydropower projects. So, but not in theory, in implementation. We want to see the implementation part. We will explore how tools like monitoring or advanced control systems or modeling are being used to improve flexibility, sustainability, and performance across the projects. And we are very fortunate to joint experts from different EU projects, Hashop and Store to Hydro by Eduard, Express Hydro and Rehydro by Elena, Hydroflex by Zoran, and Store by, how do you pronounce it? Story. Okay.
Yes. Internal debate.
Story by Alexander. And together, these projects represent a rich mix of experiences and lessons learned. And our goal is to hear directly from the partners of the projects about this issue. So I hope that this session will be an interactive session between the panelists and between the panel and the audience. So please feel free to ask questions anytime you have. So thank you again for being here. And I'd like to start by inviting each of our speakers to introduce themselves. And ladies first by Elena, please. Elena, please introduce yourself and a bit words about the projects also.
Thank you very much, Logan. Good morning, everybody. I'm Elena Paglioni. I'm senior lecturer at the EPFL and head of research at the technology platform for hydraulic machine. What we have been involved in the European projects is as coordinator in Xflex Hydro. This is a 4.5 year long project that ended last year about enhancing flexibility of hydropower station, both new and rehabilitated one. And second project we are involved in as today is a rehydro refurbishment, optimization of refurbishment situation of hydropower plants, again, for nature. In this case, the coordinator is Syntap, so we are partners for this project. Who's next?
However you want.
Yes. Hello. Hello. Yeah. Hello. My name is Alexander Presas. I'm an associate professor at the UPC in Barcelona, Polytechnical University of Catalonia. I'm an associate professor there. I'm also leading a research group associated to that institution, which is called Center of Industrial Diagnosis and Fluid Dynamics, where we basically provide services related to hydropower. Regarding the European projects, we are also have been very active in the last years. Many projects coordinated by the PFL. We started that many years ago with one project called Hydrodynamic 2. It was a small project, and then it came Hyperball, which was between 2013 and 2017. that was in the Horizon scheme. That project was coordinated by Professor Avelan. It was also very interesting project where we did some tests, some analysis in large units. Then I had the pleasure, or we as UPC had the pleasure to participate in the XFlex Hydro, as you know, a very large project, maybe one of the largest with European funding. In that project, we participated in monitoring of units, in analysis of monitoring data, structural analysis, and so on. In cases such as Vogelbrück, which was a hybridized Kaplan, Pranish 2, which is maybe the largest variable speed pump storage in the world now. And now, since last year, UPC, well, our group is coordinating the Story project, which is about innovative storage technologies in pumped storage. It's also a quite large project with participants such as EDF, EDP, these are the main operators, and Andritz and GE Vernova as manufacturers and several academic partners. Thank you.
Thank you, Don. So my name is Don Markov. I'm a professor of hydropower at the Faculty of Mechanical Engineering, St. Cyril Methodius University in Skopje. Currently head of the Department for Hydraulic Energy and Automation. We've been also involved in several EU projects. I'm here on behalf of the Hydropower project, where we were as a partner. The consortium was led by the NTNU and Professor Dalha. And the project was about developing a variable speed turbine. So most of the work was done for the parametric design tool, but we will talk later about it. Most important thing is that the need for this project was the number of starts and stops and the quick ramp up of the hydro. The project was run from 2018 to 2022, so it was a bit interrupted by the COVID. Finally, we managed to do all the work and the experiments in the lab in Trondheim. And as soon as the project was finished, the number of PVs were several times higher than the time we started. So project actually meant a lot for the development of this area. Thank you.
Thank you, Son. Ne doğru.
It's red.
Has to be red.
Has to be red. Not has to be green. It's red.
There is no
Probably better. Yeah, my name is Ilva Dujak. You know me as chair of the cross section. Beside that, I'm senior lecturer and scientist at the Turbine hydraulic machinery. Our department is part of two projects at the moment, two Horizon projects. One you see here, it's HO, Hidden Hydro, where we have the let's say development of energy harvester in Bandit, where we build up a test rig. So this is technology development, but we did a complementary project together also with Dogan on, let's say, more potential field study, which was probably more interesting and based for the HO also. So there are a lot of data were switched then to the HO. And the second Horizon project, I mean, this HO is now in the third year, so we have 1 year to go. And the second Horizon project we are involved in is the so-called Store to Hydro. It's storage project where the main idea is investigate, let's say, additional pump storage or to convert regular high-head power stations built with transistor turbines to pump storage units. So by implementing a kind of a booster pump, that's one part. And the second, let's say, area or branch we are looking for is to use run-of-river power plants as a storage possibility. So our part there is the potential study looking at Europe. Where do we have those power plants available? What is possible? And we saw in the past a lot of different or a lot of power stations which are there but not suitable, or yeah, different points of data.
Thank you, Eduard. And I see very excited audience here. So let's start by ice breaking, should I say? But, ladies first, Elena, could you tell us the integration of digitalization into your EU fund projects, please?
Yeah, so starting with X-Ray Hydro, so this project, as I said, is about extending the flexibility capabilities that hydropower can provide to support the grid reliability. And within this, we had several key performance indicators in order to evaluate how the technologies that we developed and optimized would perform in a flexible operation. So the technologies that were implemented were mainly hydroelectric circuit and reduction of batteries and variable speed. But we also consider digitalization actually as one of the technology that had been implemented. How that was integrated. So as said, this was considered technology, but at the same time, to evaluate the performance, we had also a list of KPIs like running rate, extension of operating range, and one of the key performance indicator was also digitalization level. And so we both developed technology, digital technology, that went in different directions depending on the need of the plants. It could be digitalization in terms of operational optimization. So, for instance, we integrated the real-time models of fatigue or of pressure fluctuations, vibration levels, wear and tear into the operation. So, in the communication with the control system of the machine to optimally steer again operation of machines and how different dispatch conditions should be realized in a given plant. And this was done at all kind of power plant levels. So we had 7 demonstrators. For all of them, whether we were around river, pump storage, or classical conventional storage power plant, we found a way to integrate those cloud models so that we're running real time to optimize the operation. And that allowed to classify the level of digitalization. So depending on the advanced that we had in the control. So if it was a basic one without real time, we classified this as level 1. If we had a real time component, but not fully integrated with a real feedback coming from the standard system of the brand, that would be level 2. If we had also this real-time feedback coming from the SCADA system, that would be level 3. At the same time, we also did that for maintenance purpose. So we classify as KPI a digital level in operation, but also a digital level in maintenance in the direction of having a predictive maintenance approach. And for this, in particular, collaboration with Power Vision Engineering, that has already a tool, a digital twin called Hydropower. We installed that in not in all demonstrators, but more or less in all of that. And then, so Hydropower allows for a real-time monitoring of selected parameters, namely, for instance, the pressure variations, efficiency, and all, let's say, operational parameters of machine. So thanks to this digital tool, basically this Hydropower, we were very, so I cannot say very safely because that was their proprietary development. We're able to install this successfully into 3 power plants and to show how monitoring of the, let's say, digital monitor of the plants could actually be beneficial for the better planning of the maintenance. Well, that's for Flex Hydro, trying to be brief. And regarding Rehydro, so that the scope is to have to demonstrate how a sustainable refurbishment is possible in different plants.
So, excuse me, but
Yeah.
which is newer? Rehydro is
Rehydro is
X-Flex
newer.
Hydro,
Yeah,
right?
X-Flex Hydro has completed. So finished last year. So that's why I could give a way better insight of all the, let's say, the innovations in terms of digital aspects that we did. Actually, I forgot to mention, but we call it Smart Power Plant Supervisor. So overall, this methodology, this way to integrate data into real-time models that influence both operation and maintenance, depending on then of a proprietary tool, whatever is power vision engineering, GE, Antlitz, Point, etc. These methods to integrate data into a real-time operation, so influence the actual operation and maintenance decisions of operators. We call it smart power plant supervising. So regarding Rehydro, so far, the digital developments have been, let's say, less evident because the focus, let's say, of a project is really to implement sustainable solutions in a refurbishment situation. However, definitely there is a one work package which is dedicated to digitalization. And in this work package, there are three main kind of digital tools that are under development. One is for monitoring cavitation. Another one is for erosion, so a digital model that would allow to forecast erosion due to sediments. And in one work package, we try to both correlate erosion to a decrease of efficiency, and so to be able to detect as soon as erosion happens a change into the efficiency, so that the intervention and maintenance are targeted depending on the needs and not just periodic maintenance. And then in a second step, we will try to integrate those knowledge with let's say an advanced control that considers also how erosion will evolve, and so might change the decision-making process for operations in the plant. So going both in the direction of being able to detect in advance when sediment erosion happens, and also know in advance how things look like in the machine through numerical simulation and an advanced camera, which is installed on plant and visualize basically the erosion pattern. There is also a third axe for digitalization, which is coupled with flexibility, and this is implemented in Norway. And there mainly it's about how to extend an operating range. So by predicting in advance pressure fluctuations and possible hydraulic phenomena that will happen in the machine in order to maximize, let's say, the extension of operating range of machines. So those are, let's say, the three pillars of digital tools that are currently being under development in every other. Of course, all these will be then coupled with a more informative part and a modern part coming from the environmental side. So linked to the biodiversity, linked to the sediment passed through the machine in order to do the link with also the environmental risks and optimally steer operation in, let's say, a situation that allows for better flexibility, better prediction of the technical risks, and at the same time being environmentally friendly.
So in your projects, the digitalization is used for advanced control and actually decision supporting.
In a reality, yes. And also, let's say, maintenance. So both operation and maintenance are supported by those digital tools. Yeah.
Thank you. Who wants to continue? Alexander, please.
So, yeah. I will speak about digitalization in our project, in the story project. This project has started last year, so at the end of the last year, so we are at the beginning, let's say. So what I can speak now is our intention and our goals in the different demonstrators. Also, well, it's important that we are speaking about EU projects, and most of you have participated in EU projects, and when it comes to the call and the tier levels, the story project is in the tier level 8, similar to the X-Flex, which means that practically you need to implement on the demonstrator and to demonstrate the technology, and And for the, let's say, for the fundings that we typically receive, in this scale of projects, most of them, they have to be like digital improvement, because for, let's say, with that funding, you cannot, let's say, make a new unit or something like that. Our project is called Innovative Technologies for Pumped Storage, basically, innovative technologies and control for pumped storage. It's focused on pumped storage. So one main part is digitalization. Okay. I will explain a little bit how digitalization plays a role in the different demonstrators that we have, because we have like 5 demonstrators, but there is like a common frame that we will work on it, which is some kind of digital tool we will call, which is called CATS, which is a kind of digital twin platform. Okay, it's like a kind of modular platform which will be developed by Norse, Andritz, and us at UPC as main partners, and we want to develop this kind of common framework with the main goal of the decision support. Okay. Before we had 10 minutes ago, we had an interesting talk with Edward about what is a digital twin, no? What is a digital twin? Because they have many definitions, many concepts. So sometimes it's clear, but sometimes not. And we can.
Yeah, everyone understands different things.
Yeah.
Different aspects of digital twin. For you, what's a digital twin?
Yeah, it's a good question. One thing is maybe what it should be, and what it can be if we are a little bit more realistic. So for me, like let's say a most advanced digital twin will be something that in real time, based on the internal calculations, internal estimations of the twin, can make some kind of action or important actions on the unit. Okay. For example, imagine now sediments is becoming like a problem also here in Europe in some cases. Imagine you have some case where the sediment is too high and automatically, but sometimes it can happen like in a matter of minutes or hours, and you detect that the sediment is high, and suddenly you stop with no decision of like a human person or something like that. Or it can be that suddenly, because you have done a lot of, I don't know, start and stops and something like that, you have a very weak indicator that it's indicating some potential damage or some danger for the power station, and you stop that. We know that some of these exist. I mean, for example, I'm working mainly with vibration monitoring and so on, and it's very typically that in the SCADAs we have some action levels. Let's say if the machine goes beyond 10 millimeters per second or something like that, the machine will stop. But I would say that a digital twin is some much more advanced thing, taking into account advanced methods that we have. But in this case, let's say if we go to there, we will be very happy. But our ambition is more like having a digital twin which can really influence real-time decisions. So in the short term, okay. And yeah, our context is like we have different pumped storage schemes, okay, and every pumped storage scheme will tackle a different challenge, okay. For example, we have one case which is called Vilariño. Vilariño is a multi-stage pump. As you know, multi-stage pump nowadays, they are not very common, but I think in Europe we have around 18 gigawatt of installed multi-stage pump. So it's still a quite interesting unit, and it's worth to, let's say, to investigate and to continue to develop technologies for that unit, because as you may know, multi-stage pumps have the main problem that they lack of regulation. So they are becoming less and less interesting for the flexibility. For example, which is something that in the X-Flex we went to the limits of flexibility, and multi-stage pumps cannot provide these services. So, for example, in Vilariño, what we want to develop, G is developing that, we will test how to regulate these units with the main inlet valve. Of course, this has a lot of risk because some risk because these valves are not designed for regulation. So we need to, for example, to use digitalization to be sure that the operation that we are doing is safe. It means, for example, checking the safety of the valve, advanced CFD simulation, using less simulation and so on. So, well, in that case, digitalization plays
So you plan to use the main wife as a proportional wife, right? So
Yeah.
control
In partial position, yes. Together with a very interesting solution that was also tested in Xflex Hydro, which is the hydraulic short circuit. We believe that combining this type of new regulations with a hydraulic short circuit, an old plant which was designed, let's say, for 40 years ago, with no flexibility, now we can provide some flexibility. It will not be the same as a totally new unit, for example, or a modern unit. Now, if you want, I can switch to Alkeva. Alkeva is another demonstrator in our project. Alkeva maybe is the only triple hybrid unit, hydro unit in Europe, which means it has pumped storage, it has a battery, 5 megawatt, and PV solar together integrated in the same SCADA. And yeah, of course, how to control it, how to optimize the operation of this, it's quite challenging. This is something again that, for example, in this case, GE together with EDP, which is the owner of this unit, and with the contribution of Finestec, which is an institution in Portugal, they are now formalizing the optimization problem and saying the project they will work on that, on the optimization of this type of unit. Also, I wanted to mention something that it seems very simple, but it is not. We have another case, which is the Sheila, which is a pump. This is a quite standard pumped storage in the Alps, very close to Grenoble. And one thing we want to do, well, one interest there is to accelerate the transients, fast dewatering, and so on. Of course, for that, it's very important to have reliable models, okay? One thing that we typically found in power station is that they were made in the 60s, 70s, or even in the older times. And as you know, we have only drawings, no? I mean, we don't have the digital models yet. And it's very important to make reliable models. And of course, still engineers are doing that work, maybe with the support of AI and so on. But still, I think it's a hard work to how to conceptualize the drawing and to pass into, for example, a model that can be used for CFD, for FEM, and so on. And well, if you have worked with stress prediction and so on, for example, I think it's super important the accuracy of that models, because if you are modeling some singular parts like not in a proper way, you will get a super high stress, and then like all the evaluation of fatigue, wear and tear, and so on, they are, let's say, a little bit compromised. And in that case, Kaizen, which is a partner also in the project, is doing an AI tool to check the accuracy of these models and compare with the drawing. So it's basically image recognition, which will compare the drawings with the models, with the 3D models, and to check the accuracy of that. And yeah, this is basically that. Maybe later we will talk about the difficulties in digitalization, and I will explain.
Yeah. Okay. So the last one is the aspect of digitizing, right? Digitalization. But before digitalization, you should digitalize somehow. So you get benefit of that way. Thank you, Alexander. Can we continue? So please.
Sure. Well, when you develop a variable speed turbine, it needs to be like integrated approach. So across the mechanical field where I come from, very important is the electrical area and the environment. So that's why NINA, or the National Institute for Nature, was involved to mitigate and to model the effects that this kind of regulation and this kind of operation of hydropower plants will have as an effect to the environment or the river. So let's go back to the digitalization. I'm going to speak more about the mechanical part of the project where we were involved in. So the entire Francis turbine was divided into stationary parts for the runner itself and the half tube. So and then you took care of the traditional part or the runner, and my team was in charge of the spiral casing of stationary part before the runner. So spiral casing, day vents and guide vents. And the digitalization was mostly not in the similar way as the previous cases, but mostly in the way of programming and optimization. So programming was used to obtain some optimization at the end. For the part, the function that we are going to be focusing on is the efficiency, obviously. For the stationary parts, the focus was, because the simulation was done for both CFD and stress analysis was to locate the position where the shaft, or let's say where the shaft will be for the guidance. And all this process was done using a combination of MATLAB, where most of the programming was done, and commercial software, which was in this case, let's say, SIS. But the main focus on our group was to mix all of this, and that's why we needed to make a Python scripts or to make a Python program. So what we do, we have inlet parameters, and we have some optimization function that we need to focus on at the end. But beside the university partners, there were obviously demonstrators, like this was the Toke hydropower plant, and the Statkraft and Vattenfall were the partners on the operator side. And first of all, we had the existing Toke hydropower plant model that was already investigated at the NTNU lab. So try to make a better one for it to work as a variable speed turbine. So the inlet parameters obviously are the discharge, the RPMs at nominal operation mode, and if you work up when refurbishing like this was the case, then you have the diameters already in place. So you have to work with these dimensions that are already there. Of course, if you design a new one, and this design tool that we produced, it's a parametric design tool. It can also be used for new turbines. We showed for some other turbines that are at some process of developing in my country, but also in some other partners. So the input parameters are like this, and then the output parameter is for the stress part is the position minimum stresses on the position of the guidance axis. We have a minimal stress on the guidance, and for the rotational part, it was the efficiency of it. If you go to the runner model, develop some 15 parameters. Then those parameters need to be a little bit contracted. We ended up with 9 parameters. My colleague Igor here was a PhD student with me, and now he's already received his PhD thesis at NTNU, is working at Rainpower now. Now it's Aker Solutions. He designed this part, this parametric design tool with 9 parameters. So you set the margins on all these parameters, and the process repeats itself. So the digitalization, I would say that was mostly done programming in Python, which needed to take the scripts from MATLAB and put it in a readable manner to the CFD software or the FN software. And this process should be, in the loop or continuous. And finally, to provide the geometry that has the optimal value of the function that we set in the beginning. But we said that to wrap up most of the digitalization was in a manner of programming and optimization tools using available tools for this, but also programming on the part of connecting the existing tools because they don't work by themselves.
So how long did this parameter reduction make a benefit for you for the duration of design?
Well, shortening it in days. I can say if you take out one parameter, you maybe shave a day in the calculation. And you need a lot of calculation for this, obviously.
Thank you, Zoran. So let's continue with Eduard.
Yeah, as far as I see now, all of those projects are innovation actions. So with the implementation part, is correct. Yes. The two projects we have. Yes, yeah.
It's TR5.
Terrified.
Yeah,
It's Ria.
It's Ria
Ria,
project.
okay. That's what I wanted. Yeah, that's I wanted to distinguish. It's we have to think a little bit on research innovation actions or innovation actions, and the research innovation actions go normally to this technical readiness level 4 or 5, where the innovation actions go up to 7, 8, which is then really the implementation. So it's clear that digitalization in an innovation action project plays a bigger role or a different role than in these research innovation actions. So in the research innovation action, and that's our understanding, TRL4 is up to the lab level, and TRL5 is more or less realistic environment. So you test what you are developing, either method or calculation program, whatever, um, in the lab, and then there's the question of the realistic environment. So in that project, you need, or digitalization plays then more as a role to gather the validation data. And validation data come then again from use cases, from operators, or however the project is set up. In terms of H-Hope, uh, the goal was to use hidden hydro, so places which are, let's say, not in our mind for the energy extraction or energy harvesting. And one part, which is our part, is, let's say, we focused a little bit on water distribution networks. Yeah, it's another research partner looks on, for example, water treatment plants, so open channel flow. And the basic idea is here not to use turbines or pump-based turbines or whatever. The basic idea is here to use oscillating bodies to extract energy. So very simple, but so not really on the market. So what we found in water distribution networks, for example, we know all of us, when you say there are already Pelton turbines installed, there are pump-based turbines installed, and things like that. That's true. There are already some examples there. But when we had a deeper look or a more detail, we saw that, for example, Pelton turbines or pump-based turbines are mostly installed between like a reservoir or in alpine regions where you have a reservoir and then you feed the let's say municipality or the city or town between the reservoir or a well. And the reservoir is mainly the main pipe, higher pressure or more head available, and there it's very easy to install something like a turbine. It's enough cases we have. If you go further down, yeah, and what is the focus here, for example, it's not the first part, it's more really the distribution part. So where you have a lot of piping, and we measured, and that's what I said, we had an additional complementary project, which is called Digitalization of Water Distribution Networks, where we focus really on this distribution part. And there is only source of energy is basically the velocity, water velocity, the velocity in the piping. To more or less to generate then the power, because the velocity starts to oscillate to the body, and with some kind of piezo patches what we use, you can extract then the power. But the problem is then really to evaluate the correct velocity, because in a water distribution network, normally what you can expect on data of the operator of the municipality is average daily use of water. So we use 130 liters, for example, is used per, let's say, European person per day. But it's a question of the distribution. Yeah. Then you get some literature data that says the distribution is normally used in the morning, in the midday, and in the evening. Well, this is just kind of estimation, so there is really not so easy to develop then a digital model somehow to digitalize all the piping. And just the municipality we were in, when Daniel did most of this work, had around 770 kilometers. So you are not able to digitalize every band, every, I don't know, part of that. You will never come up with that. So you have to reduce down to the main piping. And then the question of security. How much failure are you doing with, let's say, simplifying your model? And then we started to measure, and we measured, I think, 3 summer long, measured and measured and measured more and more and more and more. Before we came up with really a kind of validated model where we are now able to calculate, let's say, the flow in the piping and to detect to determine, okay, the flow velocity in that pipe is high enough to install a device like this. But on the other hand, in the project, we are developing the device and in the lab on the test rig. But the digitalization or the validation data, the measurement in the reality is needed. Otherwise, you are not able to develop a device like this. And the point is, I mean, the power extraction we have here. How is the power? It's not. It's like it's m watt, yeah, but it's a small m. It's milliwatts. But it's enough, for example, to harvest enough energy to feed the sensor. So the basic idea is then not to generate enough electricity to feed or to help the grid and so on. So the basic idea in this area, in this redistribution area, is to determine to find places where you can install a device like this. Yeah, and we are now in competition, let's say, with a battery or a solar panel, giving the power for the sensor, or you have this kind of more or less autark system where the water flow to generate electricity and then feed the sensor at the bottom. Challenge the future problems. Yeah, so that's one part. So
I think we have a problem with the online connection.
we don't let go.
It works.
Okay.
It works.
So in this case, digitalization is let's say part or the major part of digitalization is to gather realistic data to validate your models for your simulations later on to have a base for technology development.
I think the output of the workshop will be something that will help digitalization. Actually, so by feeding the sensors, its distribution network.
Because digitalization helps digitalization somehow in a way. Yeah, in the Store to Hydro project, we have it's also a research innovation action. It's again, we are responsible for the data collection to have a look where let's say the idea of technology development can then be placed. How many possible sites are available? What is the scale up of the technology which is developed? And yeah, it's quite interesting if you see how many power stations have been built. We have also to include not only the machine itself. The machine is done in TNU, but we have also to include a little bit the let's say waterways and reservoirs. Let's say investigate the entire power plant. Is it to be feasible for the implementation or the change of say of function of the power station? So again, the part of providing validation data, providing, let's say, the realistic environment for the research.
Thank you. And you have the microphone that's contributing.
Okay.
So you mentioned some difficulties on modeling the distribution network in higher resolution.
Mhm.
But I want to ask other barriers or difficulties you face within your projects for implementing digitalization.
Well, barriers. I mean, if we think on collecting the data, barriers are access to this kind of systems. Yeah, water distribution networks are normally underground somewhere. It's a limited access. It's limited access to the piping system. If you are happy, you get some kind of pressure waves where you have access. This is one point. And the second point in the simulation is if you take the data, then yes, how to set up the model, uh, how to validate. Is it based on the consumption or is it based on the pressure distribution? So it's quite challenging, and we have in this one case, I think 30 or more than 30% reduction waves. And pressure reduction waves are very sensitive. If you just change a little bit, it changes the entire network. So you can collect a lot of different situations. And during the measurement, we saw also there was a higher pressure from a firework worker, I think, and I never expected that. There was a drop of pressure, and we have seen it on sensors 5 or 6 kilometers away, through the entire network, and that gave me really wow. Yeah, that's you have to be very sensitive with the modeling, and you have also to increase the data sampling. So most of the time, the let's say data available SCADA data is nice, but most of the time not in the granularity. 15 minutes, you see nothing. We saw, I never expected, water hammers there. Absolutely crazy. We presented them to the power, to the operator, to the municipality. Said, this is happening with our pipes. I said, yes.
So you increase the resolution.
We increase the resolution and the awareness of what's going on. Yeah, that's what I have.
Sometimes nothing is better.
Yeah, probably. It comes out in the ground. Yeah.
And what about the eagerness of the municipalities or the partners to share data of their system?
Well, that sharing data is in that kind always a little bit not so easy. It's most of the time you have let's say those projects confidentially, and then we share some nominalized data for the HO when we develop that. Of course, I mean we know where it is, and we can do that. But that's very often not so easy. I think it will be on in other projects as well. Should really open data for open, say really to open the data. This is mostly not possible. That would be good, but yeah, it's data, but if you have the data, you have also the information behind. And the information means where it is, how much water flows, and so on. And so it's sometimes it's also critical infrastructure. I mean, you have to think about if you open data of a municipality. I mean, and you put it on the internet, everybody has access. Everybody knows where you have access to that, and so it's also a kind of security. I think that to share data. When you're sharing data among partners, is okay, but just really to open
Publicly.
publicly on there. But that's something I can run over. Yeah.
Okay, thank you, Edward. And Elena, please.
Yeah, and so in terms of barriers, in within Xflex Hydrof, I think development with it. Well, definitely data open to be shared as they are. We know it's not possible, as Edward said. But sharing data for the purpose of development, this we found a very good let's say, willing of sharing production data and detailed data, of course, whenever possible to have that. So production data and all pressure, discharge, whatever was measured, vibrational data, etc. All or specific campaigns that were dedicated, for instance, for onboard stress measurements, for fatigue models. Those we found a very good willing for the purpose of the development
Within the consortium.
within the consortium, of course. So European projects have normally a very good, let's say, agreement and reduction of data. So I found that normally companies are quite confident and comfortable in sharing data within consortium, within work package for the purpose of the development. Then, of course, it's part of academics to make sure that how we develop, how we disseminate in publications, for instance, does not put in evidence any particular sensitive data and make them non-dimensional, etc. But again, for purpose of making those models, those twins that would then have a real-time influence on operation monitoring, etc., we found a very good willing to share data. And I would say data source, of course, was a big deal. Definitely, in order to let operators, landowners understanding which data we need and which quality we need and the support we needed to interpret those data. Sometimes, you have production data and all those monitors parameters, but then they open bulbs and you don't know anymore exactly how they were operating the plant. So definitely having a support from the side for understanding those. We received, for instance, at least 3 years database of operations for the 7 demonstrators. So having their support in understanding how to use those data was also very important. So I would say that was not a barrier, but definitely a challenge to interpret this correctly. Maybe what I would see more as the barrier can be having the integration on those tools that we might develop into their commercial operation. And this, it depends quite a lot. We saw that some operators are more open to take maybe some risks. One of the big, let's say, issues is the IT security. So introducing, for instance, an external laptop with a code running for real-time monitoring or for real-time control of their machines was often something that was complicated from an IT perspective to make the security check and also the remote following up from either companies or from the academic partners. Sometimes it was just decided to test it, but to not install, to not taking the risk. Sometimes you feel more comfortable if there is an operator pressing the button instead of having a digital model control your machine. And this is maybe a philosophy that will change hopefully in the future, but definitely I see this as one of the possible barriers. So to not being all operators ready to have digital tools running your machines. Even if we sell it as it's an optimal way, of course, there can be still margin of error. So I think this also goes in the direction of making those more trustable, demonstrating which are robust enough to be integrated in commercial operation.
So they are the operators. We cannot blame them because their priority is to operate the machine and earn money. And perhaps it's our duty to show that, to show them the benefit, as you said, and it's reliable.
But there are some cases where we accept it. For instance, if I think to the two demonstrators in Portugal, Alqueva and Alto Lindoso, they now run with an advanced joint control where this optimization takes place. And there are others where we tested it, but so we found the optimization that was successful, but still, let's say, there would need more, let's say, efforts, more more development behind to make these fully compatible with the commercial operation. So I think from one side, definitely there is the willing of having these implemented on the site, and then on the other, maybe sometimes one of the barriers is, are you ready to take the risk of changing the way you operate?
Yeah, good question. Yeah.
Okay. The point you just made is very, very good because operators need to operate and make money. I guess, Elena, since you have at least one or few case studies that they accepted to take it, I guess the best is to ask them to put together as much data operational as possible to show annual generated power improvements through these tools and optimization, and also immediately answers the point of Dogan that translates into a significant increase on annual generated revenue. And this is exactly what I have done from my experience in a project in Japan, where they had a super efficient, mid-90s% efficiency Francis machine that, because of earthquakes and volcanic dirty water, sandblasting a machine and stoppages and reducing the annual generated power and revenue. I replaced them with new designs from the UK. I did with lower efficiency, but able to withstand that. I replaced mid-90s Francis to mid-80s turbo impulse machines. Just one to check if it works. And immediately the answer was to maintain a lot of data as a reference. And they had an increase of 30% annual generated power and revenue. This data was used for a series of similar projects in Japan. Based on that, I would have thought if you follow a similar way with your project, perhaps it will give you the references required to further adoption of the software to please the developers that Logan is referring to. Thank you.
Thank you, George.
Well, of course, the solution, it's definitely true that operators want to make money, but definitely those tools, whenever integrating, demonstrated before being integrated that we will allow the operator to earn money. Otherwise, of course, that's the base, right? Otherwise, nobody would install it.
Right.
And then money can be seen different way, can be of course being operating, so increasing the revenue from participation to markets. But operators today also gives value to maintenance, risk, avoided risks of rupture. All those are factors that today give value to technology. So reducing the risk, for instance, of making your plant more available, then something that operators today are able to quantify as benefit. So definitely, I'm not blaming the operators for not installing all technologies. What I just want to mention is that there are some bugs sometimes when to go, you're ready with your solutions, it's robust enough, it has been installed in our plant, so it demonstrated that in other conditions was effective, but we all know that every power plant is different. So also the use and the importance that a power plant can have for the operator is different. It can be, let's say, one of fleet, or it can be the one of your fleet that you really need in some conditions as key for your operation. So sometimes those represent barriers, but even though you have a perfect tool that works, they need to have time to digest, which are the technological developments, and also be suitable for changing, let's say, the way of standard, or let's say, standard or conventional way to operate.
Okay. Thank you, Elena. Let's continue with Alexander. Do you have any difficulties, Alexander, in your projects?
Yeah, many difficulties. I mean, and I will try to summarize it.
You have a list of difficulties, like you say.
No, well, first, regarding the operational data, I totally agree with Elena. Operators are typically, at least operators are typically works and are used to work in this type of collaborative projects. They understand that they need to share something. We need to start with something and to optimize, to make optimizations based on something. Okay, so yeah, for that I think it's quite a positive experience. Then I think Elena also mentioned at the point of cybersecurity. This is a big point. I mean, especially for example for academic partners or other type of partners which are not directly the operators, no, where you want to install any kind of system which is somehow connected to their devices or is taking data from the SCADA and so on. Yeah, it's becoming, and well, it was already an issue, and it's becoming even more important. I can quantify, for example, in the Hyperbole project, we lost half of the year of the data because of that. I mean, we went to, and in that case, the demonstrator was in Canada, so we had to travel from Europe to Canada. More than one team install the system. You go back to Europe, you expect that it will work, and then, well, at the end it's solved, but it means like a second trip to there to speak with the IT.
Additional budget.
Yeah, additional budget. So this is a difficulty. Also in the X-Flex Hydro, the same issue. In this case, we were lucky because the demonstrators were in Europe, only 1,000 kilometers, but yeah, again, a second trip to solve the issue. And at the end, it was solved, but it's something that we need to consider when we install this type of systems, okay? Then, well, related to the data collection, here it's also very important to mention the quality of installation, the importance of having reliable sensors is also very important. Now I'm thinking, for example, we were speaking about sediments and so on, and the way to monitor sediments is quite sensitive because, okay, normally we install sediment sensor is because we are working in a harsh water, and yeah, because of that, the water itself it can produce some damages to the sensor, no? And now it's also interesting that, for example, Android wants to install in the frame of the project a sediment sensor in La Rance, and in this case we have the extra problem of the biofouling, and the biofouling which is totally attached in very few months to the sensor, no? And you need to expose the sensor to the water because you want to measure set. So I wanted to comment this, that sometimes the data collection is quite important. Then, yeah, well, related to validation and so on. Yeah, it's somehow related, no? I think Eduard mentioned about this validation, the word validation. I think the most reliable your installation is, which is sometimes not super trivial, is something that will help, no, to have more reliable validation. And then I want also to share a little bit is my personal experience in this project, but also in other, let's say, more industrial projects. It's like, as you know, these big operators, they work at very different levels, no? And sometimes you convince somebody on, let's say, on the engineer level to install a predictive maintenance system and so on. But then when you go to the power station, you have to make the people there to understand that what you are doing is useful. And on the other important part is to show them that you will don't disturb so much their regular activities, because at the end, I would say I have found this in many cases, they are the head of the local power station, even if this power station is very important or something like that. No? I mean, at the end, you have to manage with that and to be, I don't know, to be respectful with the jobs that they are doing, because they have a lot of pressure. For example, during the overhauls, is the typical periods when we install this type of things. Yeah, they have to give back the machine, I don't know, in 2 days. And many times, well, I have the feeling that you are somehow the last priority, which is totally understandable, but it's let's say a long-term benefit. Okay, so something here I can mention. It was 1 month ago, something like that. Before we had a contract with a big operator in Spain to make a kind of predictive maintenance of the pump turbines, based on vibration sensors and so on. Now we are not more in charge of the data management and the data analysis, but still we have some contacts for research projects and so on. So time to time we go to there and we do some tests or we take some data. And they had to install a displacement sensor on the shaft. Okay, something very very simple. And I told them, yeah, please install the sensors. Not for me. It's for you, because I don't receive anything for that. It's just that let's say somehow these kind of machines I know them since I was like very young, since 15 years ago. So I respect that machines and said, please, now that you have the time, install that displacement sensor. Okay. This displacement sensor was a radial displacement sensor. So if you are familiar with bearings, tolerance, and clearance, more or less, I would say it's 0.2, 0.3, 0.5. It depends a little bit on the diameter of the shaft, no? And then 3 weeks later, they started the machine. It was like a fire in the machine. I cannot say many details about which machine was, but it was a pumped storage, big one. And well, they started inspection and they found that the gap now is 3 millimeters on the bearing. So you can imagine that this will mean
3 millimeters.
3 millimeters there.
They should treat at 0.3.
Yeah. So 10 times. So, and this could have been prevented with just a displacement sensor, which is 200 euro sensor. Of course, then the system and so on, and half a day of work or less. But when you are doing the overhauls, or in the, let's say, in the strategy of the company and in the planification of the company, this has to be considered as a benefit, no? And yeah, we have a lot of operators, different realities, but I have found this as a barrier to really understand the benefits of this type of more advanced digitalization, which is like maybe you will not see the benefits in next day and so on, but overall, I think the benefits are very clear. And yeah, and then on a later stage, I think that like the adoption of these strategies or of this optimization and of the benefits of digitalization, it's something that it's also challenge. And well, and to summarize a little bit what I'm saying, it's like the way of passing from a kind of more periodical maintenance, that typically is being done in most of the power station to trust really in predictive maintenance is one of the challenges, and I think we are still to go and to show that these benefits of digitalization.
Thank you, Alexander. Let's hear from Zoran before we proceed with future directions.
Yes, I'll try to be brief. So, having in mind this was a research and innovative action, and a couple of PhD thesis came out of it. So, Maria Lazarevich and Philip Stoikovsky's thesis. But most of the challenges were in the research area. First of all, the validation. When we are designing a variable speed turbine, and all you have measurements for a fixed speed turbine, then you have to simulate what will happen when variable speed is implemented. So, to be honest, we have very good collaboration with the company, with the operators. They provided us with a lot of results from the turbine, and the models that we made then were measured on the test rig, and then okay, the normal issues and challenges when you're key model tests usually exist. But on the digitalization part, I think that the biggest challenge was that all these software that I said, so MATLAB, Python, or I don't know, some commercial CFD software, have different frameworks, and it's very challenging really to code something, take the data from here, and prepare such a file that this usually commercial software must read. So the coding was probably the biggest issue in this research area. And then we found out that some of the commercial softwares have only some versions that read some files. When you crisscross everything, then you have to find the ideal combination. Which file to produce from MATLAB, which file to produce from Python to read the MATLAB file, and then to produce a curve file for the geometry for, let's say, for us. And the other problem was that if you need to change something, okay, then the loop starts and it's fine. It creates several geometries, calculates the functions which you're chasing after, and then you get an optimized version of geometry. But if you need to change something, then you need to go again to every of these steps. So there's a lot of human interaction in all of these steps before it became self-sufficient or it can run itself. So the most of the issues that we had were connected with this programming part, to be honest.
Okay. Thank you for sharing your experiences. For asking our speakers about the future directions. Any questions so far? Would you like to have any questions or any online questions? Yeah, Sebastian.
I have a question regarding to the variable speed. The project generally for the classical design, we have the parameters, we have the select the speed and the diameter results. For that reason, that is classical design. Based on the developments you mentioned to Tokyo, if I remember right, it's a high-end machine.
Yes.
And it's already designed. And you have some constraint regarding to the existing. That is the discussion. Maybe if you can share with us, which are the benefit and developments take into account. We have some constraint because the machine is already designed. That is maybe one discussion, and if you can share with us some conclusion regarding the project, because the general variable speed opened a new world in the hydraulic machinery, and that is one part to discuss what's happening in the future and what are our, let's say, chance in order to look different we already have in mind. Thank you.
Thank you, Sebastian. So, as much as I can share, the point was that usually high-end transistor turbine, when starts working in off-peak design off-peak conditions, they usually turn it off. So it was a lot of starts and stops. The point of the project was to have decent, let's say, or high efficiency in off-peak design, off-peak points. And the results were like this. So first of all, the constraints were that you cannot change the dimensions that are already in place. So the runner must fit in the same position where it is, or the guidelines must fit. You can change the geometry, but they must fit inner and outer diameters. So the main optimization is to have higher efficiency at off-peak points. And this was the result that we have, and the model showed this. So the outcome is that they can run with higher or lower speeds without turning it off. Especially having in mind all these variable renewables that we have. Okay, maybe not for Norway, but still, this can be used anywhere to shift, to decrease the RPMs, and to have decent efficiency in this point.
And on efficiency, I'm not looking to the pressure passage stability of the HBS.
This is the other thing that we're doing. Also, when you discuss the transient regimes, they are very challenging. So overall, the results were that shouldn't be worse. Let's say the situation with all of this shouldn't be worse.
Okay, thank you for the answer. And one more question.
And what is the range of the change we have over evolution?
Not about 20%, let's say.
Lower.
Yes.
You're not going lower.
We can go a little bit higher, but lower probably about 20%.
One more question.
Hello. Maybe a question for Mrs. Elena. You were mentioning there is I want to ask for this diagnosis system. Like the changes in performance of the hydro unit due to abrasion was considered to, for example, it can be mechanical attrition, other like attrition effects, which lower the performance, only abrasion. How to differentiate? So there was some mechanism to differentiate between effect due to abrasion and other effects.
This is in Reality project, so it's at the quite early stage. We have been working on this since 1 year. And there are different considerations and different studies that we are doing. In TPFR, what we are doing are numerical simulations to understand, first of all, how sediments differently distributes in a jet of a pellet. Because we saw that the ideal jet of hypothesis would not be characterizing wall of erosion. So how sediments distributes in jet, so the fluid dynamics and fluid structure interactions of particles from sediments with flow. And then the hydroabrasion on both on the buckets mainly. So those are computed numerically, and in parallel, HS in Siena is doing numerical simulations without particles, but with an eroded geometry. In this case, so simulations do not have the complexity of the two-phase sediments and water, but at the same time they can better perform in predicting how the efficiency, the torque changes based on the different patterns that are reproduced on the geometry. This is then validated, but the validation is not done yet because so far we are at the numerical simulation stage. So will be validated with a measurement on site where we are measuring how erosion pattern is modified. We are not only looking at change in efficiency, but also in change in vibrations. This is how, so you see on the web trying to target how to prevent, to detect erosion. And so there will be measure on site, and then there is an intelligent camera developed by Hendrix. And this camera basically is visualizing with a high-speed acquisition system the sediments conditions that pass through the distributor of the Balkan, and coordinate that with virtual patterns. So those three elements together, so two kind numerical simulations and the on-site test will hopefully give a tool that is able to detect erosion and integrate that knowledge into the decision-making process.
Thank you.
You have an online question. Pavel, would you like to ask yourself or?
Oh, hello. Nice. Thank you for a very informative discussion. I would have a question that I also put online to the chat.
So let me ask on behalf of you. So what are the major bottlenecks of digitalization application from point of researcher and plant operator? So anyone? Alexander, would you like?
Okay, I think already mentioned it a little bit, but yeah, I think it's very important is cooperation in all the levels between researchers. So yeah, researchers and plant operators.
So let me ask strictly. So how can researchers reach plant operators for a possible project?
That's a good question. I don't know if somebody has to answer this question. Well, I would say that in my case, now I'm leading this group in the Polytechnical University of Catalonia. We already had some cooperation in the past, and it's a long-term cooperation. Or in case of European project, for example, one initiating project, and then for the upcoming project, it's also very beneficial, like to have work with these operators and to show them something what you are doing, and that what you are doing, they can get some benefit, and in terms of European project that you are, let's say, working in a cooperative manner and so on. I think that's very important. I would say it's not super easy to start this type of cooperation. So I don't know if somebody else wants to.
I think that's everywhere the same. Yeah. If you look to the Austrian, I mean, it's always a kind of personal network, personal connection where it starts, and then, of course, and it develops. I mean, what I presented today is the Horizon project. We did a similar project on a national level. What you did, and we installed also sensors and measured. We measured 9 months the entire power plant in raw data. So it was around 7 terabytes of data at the end. There's another digitalization aspect then in data handling, but coming to that, how to, what I do, I go there, I know the people, and go there and ask them and talk to them, ask them what kind of challenges they have and how we can cooperate. But I'm pretty sure if Alex comes to Austria and goes to the operator, he will say no. Vice versa. Yeah, that's reality. That's probably or why it's good to have Horizon projects to interconnect more, and then of course those connections starts.
Yeah, you're right. Thank you. Any addition? No, would you like to say?
I definitely share the same opinion. Maybe what we can add as bottleneck, not from plant operator, but this is really from the researcher, is the understanding of what's happened in what we are modeling. So of course, so far we discussed mainly on the barriers that we had in the projects and in the implementation of the solutions. But let's not forget that from a research perspective, we need to carry out the fundamental research that allows for building those models. And this is definitely one. So that's a gap, which is there. And that's also why we need the research activity. So I would not call it maybe as a barrier, because it's, or let's say, a challenge, exactly. So, and you need to have ideas, you need to understand the physics. So if I think, for instance, to the monitoring tool for cavitation, erosion, etc., you might get the best data set so that you might think of, but still you need performing students that develops and push the literature further. And definitely for this, there is a need of projects, and out of those results that I mentioned from X-Flex Hydro, for instance, we now have 4 new national projects in order to better understand some part of the physics, because one of the challenges, and maybe this can be one of the barriers, is that if we want those models to be real time and to be compatible with the operation, they must be computational efficient. They must quickly respond to the needs. And you cannot think of a full 3D model of all the components of the plants. That would take months if you think, I don't know, to a startup seconds to be solved. So definitely also going the direction of reduced order models, understanding what is the relevant physics, and building new numerical tools for this purpose is one of the barriers that, of course, research hopefully will be able to answer in the future.
Thank you. While you have the microphone, let's continue with one or two sentences of your future directions on digitalization. So what will happen in the coming future?
So as I said, so this doesn't want the link with what I just mentioned. Definitely, we understood what are the limits of the current methods that we have been developing. If we think, for instance, to predictive maintenance because of fatigue during operation of a high loading, where does high loading come from? Why are we able to understand that from a fundamentals perspective, so that his understanding allows to build better models that maybe are less accurate of all parameters that we might think, but we are really at top notch for what we need for let's say fatigue, for instance, or the maintenance due to fatigue during operation. And so from our perspective, so this is one promising line of research. So for instance, I currently have 3 national projects that investigate different parts of those of these kind of developments, going into fatigue during startup, during a switch mode from turbine to pump and vice versa, understanding better erosion, so physically what happens, what are the driving parameters, how can we improve the current models to decrease the computational time of those simulations. And for all these, of course, having data from site helps, but also have data from reduced scale model experiments is fundamental, because there you can really better parameterize the phenomena, you can better visualize the phenomena. And if you want to have those numerical models which are efficient, you definitely need a very accurate validation, but you cannot reach with data on site. So you must think about experiments in the lab in order to fully understand what's happened physically to, let's think, for instance, to cavitation. Definitely you will never be able to picture how all the different cavitation patterns that we have in the machine on site. So for that, we need to devise new experiments at reduced scale. And those are a little bit the line of directions that I see in order to better support from the machine side, of course, because that's our focus. If somebody has another domain, of course, that's not the only component of a hydropower station, but from the machine side, where we focus our research, those are for me the mainstream line of research. But at least I wish to pursue my.
Thank you. Thank you, Elena. Alex.
Okay, yeah, so
with one or two sentences, please.
Okay, just to say one, make this differentiation between basic research, which I think it's quite important. Particularly, I'm very interested in the resonance mechanism and to understand, for example, things like resonances in power turbines, which I think something that we are still investigating. I think still it's very challenging to know when a pump turbine runner is under resonant state. It's something that what I have heard from some cases that it's still challenging, and then I'm happy when somebody says, "Oh, I read your paper from 10 years ago from your PhD, which explained that mechanism, and thank you." And well, this is also which highlights the importance of basic research. And more on the operator side, I would be happy, during the story project, for example, if this tool that we are developing together with Norse and Andres and so on, it's finally useful after these 4 years, and that's what EDF or EDP wants to keep this tool and because it's useful, because well, we would like to develop something useful for the future of hydropower and for the safe operation of hydropower, which is nowadays, as you know, doing very challenging things with a lot of start and stop, transients, and so on.
Thank you, Zona.
Very shortly. So one aspect is we identified some gaps in the curriculum, and then we need to fill it with this digitalization part. This is very important in my opinion. The other thing are the transient regimes. We need to investigate them further. And the third one is the so-called digital refurbishment. I think that this is the way to show the operators how things should be done in the future. Thank you.
Thank you. Hydro?
I'm the last.
Yeah. Closing speech.
No, when everything agree to that, what you said, what is needed in terms of technical issues and research issues and so on.